There is a line in space. You cannot see it. It has no physical marker, no wall, no fence, no change in color or texture or temperature that would tell you it was there. It is invisible, perfectly invisible. But cross it, even by a single meter, even accidentally, even without noticing, and nothing that exists in the known universe can bring you back. Not a rocket, not light itself, not the most powerful force ever conceived. Because on the other side of this line, every path, every possible trajectory through space and time that physics permits leads in one direction only, inward, toward the center, towards something so dense, so extreme, so fundamentally beyond the reach of any equation our civilization has ever successfully written that we gave it a name that is really an admission of defeat, the singularity. This line is called the event horizon, and it is the boundary of a black hole, the point of no return, the moment at which the escape velocity, the speed you would need to travel to break free of the gravitational pull, exceeds the speed of light. And since nothing travels faster than light, nothing escapes. Not matter, not energy, not information, not you. We have studied black holes from the outside for decades. We have photographed their shadows. We have detected the gravitational waves produced when they merge. We have watched stars orbit them and measured the distortions they create in spacetime. But nobody has ever told us, with complete scientific certainty, what happens on the other side, what happens after the event horizon. Today, we are going in. Not physically, not yet, but as far as physics, mathematics, and the deepest thinking of the greatest minds in the history of science can take us. And what we find inside is stranger than anything the outside could have prepared us for.
Let us be specific about the black hole. There are different kinds. Stellar mass black holes, formed from the collapsed cores of massive stars, contain perhaps 5 to 50 times the mass of our Sun, compressed into a region perhaps tens of kilometers across. The event horizon of a stellar mass black hole is a place of extraordinarily violent tidal forces. The gravitational gradient, the difference in gravitational pull between one side of your body and the other, would be so extreme at this scale that you would be spaghettified long before you reached the event horizon. Stretched, pulled apart, reduced to a stream of particles and radiation before the crossing even begins. So let us choose a more hospitable black hole for our thought experiment. A supermassive black hole. One with billions of solar masses at its center, like the ones that sit at the hearts of most large galaxies, like M87, the black hole that was photographed for the first time in 2019, like Sagittarius A star, the 4 million solar mass black hole at the center of our own Milky Way. In a supermassive black hole, the event horizon is enormous, millions of kilometers across. And crucially, because the size of the event horizon scales with the mass of the black hole, the gravitational gradient at the event horizon of a supermassive black hole is actually manageable. You could, in principle, cross the event horizon of a supermassive black hole and not immediately die. Not immediately. So, you are falling toward the event horizon of a supermassive black hole. From the outside, from the perspective of someone watching you fall, something extraordinary appears to happen. You slow down. As you approach the event horizon, the light carrying information about your position takes longer and longer to escape the increasingly deep gravitational well. From the outside observer's perspective, you appear to decelerate, to slow, to hover, to freeze at the event horizon, your image redshifting, shifting toward longer, redder, dimmer wavelengths as the photons struggle against the gravity. You appear to stop at the boundary, frozen there, dimming slowly as the light from your position becomes increasingly redshifted and increasingly difficult to detect. From outside, you appear to remain at the event horizon forever. But from your own perspective, this is the extraordinary part. Nothing dramatic happens at the moment of crossing. No flash of light, no sensation of a boundary, no alarm. no change in the immediate environment that tells you the line has been crossed. You fall through the event horizon the way you might cross an invisible line drawn on a field, without feeling it, without knowing precisely when it happened. And yet, everything has changed. Because now, every path forward, every possible direction you could travel, every trajectory that the laws of physics permit, leads toward the singularity. The future, for you, is no longer ahead of you in the way the future normally is. The future is inward. The singularity is not a place in space you are moving toward. It is a moment in time you cannot avoid.
Outside a black hole, space and time behave in roughly the ways we expect. Space is the direction you can move: forward, backward, left, right, up, down. 3 dimensions of spatial freedom. You can choose to go toward something or away from it. You can accelerate or decelerate. You can turn around. Time is the direction you cannot move against. It flows in one direction, forward, from past to future, and no force or technology can reverse it. But at least time feels external to you, passing around you, something you move through rather than something you move toward. Inside the event horizon of a black hole, this relationship inverts. Mathematically, and this is not a metaphor, this is what the equations of general relativity actually say. Inside the event horizon, the radial direction toward the singularity takes on the character of time. It becomes the time-like direction, the direction of inevitable forward motion. You cannot avoid the singularity for the same reason you cannot avoid tomorrow. Not because something is pushing you, not because the gravity is irresistibly strong in a conventional sense, but because the singularity is in your future. It is when you are going, not where. This is one of the most profound and disorienting concepts in all of physics. The singularity is not a place, it is a moment. A point in your personal future that you are moving toward the way all of us move toward next Tuesday. Not because we are being dragged, but because time flows and we flow with it. And between crossing the event horizon and reaching the singularity, you have time. How much time? It depends on the mass of the black hole. For a stellar mass black hole, the time between crossing the event horizon and reaching the singularity is microseconds, far too short for any experience at all. For a supermassive black hole, billions of solar masses, the time is measured in hours, potentially days. You are inside a black hole. You are falling toward a singularity that is your inevitable future. You have hours. What do you see? The universe behind you, the entire observable cosmos, is still visible. Light from outside can still fall in through the event horizon after you. The universe does not disappear from your view the moment you cross the line. But it looks different. The light from outside arrives compressed, blue-shifted, concentrated into a shrinking circle of light directly overhead, the direction back toward where you came from. As you fall deeper, that circle narrows, the entire universe compressed into a smaller and smaller patch of light above you as the geometry of space-time inside the black hole focuses all exterior light into an ever-tightening cone. Around you and below you, closer to the singularity, darkness. Not the darkness of empty space, the darkness of a region from which no information can travel fast enough to reach you. You are seeing the universe from inside a one-way membrane. And the tidal forces are building. Even in a supermassive black hole, where the tidal forces at the event horizon were gentle enough to cross safely, they increase as you fall deeper. The singularity is a point, a genuine mathematical point of infinite density, and as you approach it, the tidal forces increase without limit. Spaghettification, inevitable, coming. In those final moments, your body would be stretched and compressed simultaneously, not destroyed explosively, drawn out, attenuated. The atoms of your body pulled apart in the direction of the singularity, compressed in the perpendicular directions, as the tidal force gradient becomes first dramatic, then absolute. And at the singularity itself, the equations break. The singularity is not a mystery because we have not thought about it carefully enough. It is not a mystery because our instruments are not powerful enough to probe it. It is a mystery because our physics, the best, most accurate, most experimentally verified description of reality that human minds have ever assembled, produces nonsense when applied to it. The equations of general relativity, which describe gravity and the curvature of space-time with extraordinary precision everywhere they have been tested, reach the singularity and return infinities. Infinite density, infinite space-time curvature, infinite gravitational field strength. In physics, infinities and equations are rarely literal. They are usually signals, signs that the theory is being applied outside its domain of validity, that something is missing from the description, that a more complete theory would handle the situation without infinities and give a finite, meaningful answer. The singularity is where general relativity breaks down. And the theory that should take over, quantum mechanics, which describes the behavior of matter and energy at the smallest scales with equal extraordinary precision, is mathematically incompatible with general relativity. Two of the most successful theories in the history of science, each one tested to extraordinary precision in its own domain, each one agreeing with experiment to many decimal places, and at the singularity, they collide. They cannot both be right. And we do not yet have the third theory, the theory of quantum gravity, that reconciles them, that describes what happens to space-time at the Planck scale, where quantum effects and gravitational effects are both important simultaneously, that tells us what the singularity actually is. String theory has been a candidate for decades. Loop quantum gravity is another, but neither has yet made experimentally testable predictions at the singularity that our instruments can verify. The singularity remains at present beyond the reach of our physics. But this is not the end of the story, because there are proposals, ideas, theoretical frameworks that hint at what a complete theory of quantum gravity might say about the singularity, and some of them are extraordinary. One possibility, the singularity is not a point of infinite density, but a region of Planck-scale quantum spacetime, a foam of virtual geometry fluctuating at the smallest possible scales, where the very concepts of space and time lose their meaning, and something else, something our current language and mathematics cannot yet describe, takes over. Another possibility, associated with loop quantum gravity, is that the singularity is a bounce. The collapsing matter does not reach infinite density, but reaches a maximum density set by quantum effects, and then rebounds, explodes outward into a new region of spacetime, a new universe, inaccessible to the old one, born from the compressed remnants of a dying star or a falling object. Under this framework, every black hole is a seed, a birth event for a new universe entirely disconnected from our own. Another possibility, associated with string theory and the work of Stephen Hawking, is that the information that falls into a black hole is not destroyed at the singularity. It is preserved, encoded in some form, and eventually released as the black hole slowly evaporates over astronomical timescales through Hawking radiation. This is the black hole information paradox, one of the deepest, most debated problems in theoretical physics, and its resolution, when it comes, will almost certainly require the complete theory of quantum gravity that we do not yet have. The inside of a black hole is not a place where physics ends. It is a place where our current physics ends. And what comes next, what the complete theory will say, may be the most important scientific discovery in the history of our species. We began this journey at the event horizon, an invisible line, unremarkable to cross, impossible to return from. We fell through. We experienced the inversion of space and time. We watched the universe compress into a narrowing circle of light above us as we fell toward an inevitable future. We felt the tidal forces building, and we arrived at the singularity, the place where every equation we have fails and every answer dissolves into infinity. And then we stopped. Not because there's nothing more, but because we have reached the boundary of what human knowledge currently extends to. The event horizon is not the limit of what we can think about, but the singularity, for now, is the limit of what we can rigorously describe. And sitting at that limit is an extraordinary place to be. Because limits in science are not permanent. They are temporary. They are the places where the next generation of ideas is built, where the new questions live, where the discomfort of not knowing eventually, if you sit with it long enough and work hard enough, transforms into the breakthrough that changes everything. Newton's mechanics was the limit of physics for 200 years. Einstein showed the way beyond it. General relativity and quantum mechanics have been the limits for a century. The singularity is where the next Einstein, the next breakthrough must go. And we are closer than we have ever been. The detection of gravitational waves in 2015 opened a new window on the universe. The photograph of M87* in 2019 showed us for the first time the shadow of a black hole's event horizon, actual visual evidence of the most extreme object in the cosmos. The ongoing work of the Event Horizon Telescope is giving us more. Higher resolution, more detail, more data from the most extreme environments in the universe. Hawking radiation, if it can be detected, if the technology to measure it can be developed, would carry information encoded by the physics at and near the singularity. It would be a message from the inside, written in quantum effects, readable, in principle, by an instrument sensitive enough to detect it. We have not yet built that instrument, but we are thinking about it. And thinking about it seriously, rigorously, mathematically, is how every great discovery in the history of science began. What happens after the event horizon is the most important unanswered question in physics today. Not just because black holes are extraordinary objects, not just because the answer will tell us what happens to matter and information and space-time at its most extreme, but because to answer it, we need a theory that unifies the two great pillars of modern physics, general relativity and quantum mechanics, gravity and the quantum, the universe at its largest scale and at its smallest, the theory of everything. The question hiding inside a black hole is the question that, when answered, will give us the most complete description of reality that our species has ever achieved. Every time we have expanded our understanding of what happens in the most extreme environments, the interior of stars, the moments after the Big Bang, the quantum behavior of atoms, we have discovered something fundamental. Something that changed not just our picture of that specific environment, but our understanding of the universe as a whole. The event horizon is the last great frontier. And we are at its edge, not crossing it physically, not yet, but reaching for it with mathematics and imagination and the relentless, unstoppable human drive to understand what is on the other side of every line we are told cannot be crossed. The singularity is waiting. Physics is not finished, and the universe, as always, has more to say.